This is the morning of the 17th of November, 2025. A clip by WYMGX PORTUGUES. Something is wrong with the official report. Air India 171. This plays for 25 minutes. I might do this in two parts, depends on what I hear. So let's have a listen.
An Air India Boeing 787 lines up on the runway at Medabad. 9 hours to London ahead. 71 cleared for takeoff. The aircraft is cleared for takeoff and accelerates down runway 23. But seconds after takeoff, something inside the cockpit goes terribly wrong. Why did you switch off? I didn't. And the flight is doomed before it even climbs out of sight. To understand what really happened, we built a complete 3D reconstruction of the final moments. We recreated the city, the airport, the crash site, and the aircraft's trajectory, stabilizing and matching every frame from the available footage. And we found something interesting in the simulation that doesn't match what the preliminary report says happened that day. This is a reconstruction of Air India Flight 171. 12:30 June 12, 2025 Medabad. Boarding begins for India Flight 171 to London Gatwick. This is one of only 5 weekly flights connecting Gujarat to the UK's huge Indian diaspora. On board today are 230 passengers and 12 crew members, business travelers, students, and entire families. But this plane will never reach London, because at 1 p.m. the cockpit doors will close and by 1:40 p.m. the aircraft will have disappeared. The crew reports for mandatory alcohol tests at 11:55 a.m., and both pass without problems. In command is Captain Sumit Sabaril, 56 years old, with over 15,600 flight hours, more than half of them on the Boeing 787. To his right sits First Officer Clive Sear, just 32 years old, with 3,400 hours in total and 100 on the Dreamliner. Aviation runs in his veins. His mother flew for Air India for 3 decades. It's an experienced crew, flying a familiar route, but in less than 15 minutes a small action between their seats will decide the fate of this flight. At 1:10 p.m., refueling is complete, baggage is loaded, boarding is finished, and the cabin doors are closed. The crew has loaded 54,000 kilograms of fuel for the 9-hour flight to London. The plane weighs over 200 tons. It's heavy, but still within operational limits. Today is a hot day. The temperature is 36. Hot days, like today, make the air less dense. There are fewer air molecules available to support the wings and also less oxygen for the engines to use. What this means is that the plane needs more speed to take off. And given that the plane is heavy, Air India 171 will need to use the entire 3,500 meters length of runway 23. But having said that, this is also well within the capabilities of the Boeing 787. The plane begins pushback at 1:18 p.m. On the platform, the captain moves the 2 engine switches to run. Both engines rev with their characteristic whistle.
India 171, taxi via Papa, Romeo 4, line up and hold on runway 23.
While the aircraft taxis down the runways, the crew completes the pre-takeoff check stripes. The speeds to observe are V1 at 153 knots, VR at 155 and V2 at 162 knots. After backtracking on runway 23, First Officer Kander executes a 180 turn to position the aircraft for takeoff. At the far end of the runway is the airport perimeter wall and beyond it is the dense Meghaninagar neighborhood. Visibility is 6 kilometers. Winds are light at 240 and 6 knots. It's a perfect day for flying.
Air India 171, winds 240, runway 23, cleared for takeoff. Cleared for takeoff, runway 23, is 171.
Takeoff clearance is issued at 13 hours 37 minutes and 33 seconds. 4 seconds later, First Officer Kander advances the power levers. The plane begins to roll down the runway, and the countdown to disaster begins. What you are about to see is a detailed 3D reconstruction of the final moments of Flight 171, recreated second by second, frame by frame. This is Sardar Vallabhai Patel International Airport, built to scale 1 for one of the real-life airport. This is runway 23 here, and the crash site is 1.7 kilometers away from here. These two red structures are the student cafeterias, referred to as buildings A and B in the provisional report. Behind them are the 4 student dormitories, referred to as buildings C through F in the report. The tall chimney here is the Army Medical Corps incinerator, and the small grove of trees right next to the chimney would be the first point of contact. It is 1:38 p.m., and the BJ Medical College cafeteria is full of students having lunch. At the nearby airport, Air India 171 has just taken off and is now at its highest point, just above the airport's perimeter wall. As it crosses the wall, the plane begins to lose altitude and starts to drift to the left. This camera here is positioned exactly on the extended center line, and the leftward drift is quite clear. I will explain my theory about this drift later in the video. Just a minute later, at 13 to 3909, the plane is almost near the ground and makes first contact with a group of trees within the Army Corps complex. Almost immediately, the nose landing gear hits the incinerator chimney and detaches. The main fuselage is still in one piece and continues moving forward at 150 knots. Note the attitude of the plane here. It's nose up at 8 degrees. What this shows us is that the pilots, even at the last minute, were pulling back on the control stick, trying to get the plane to regain altitude. They were trying to get over the buildings, but they couldn't. At 13 hours 39 minutes and 10 seconds, the right side of the fuselage strikes the northeast wall of Building A. The right landing gear and tail section receive the greatest impact here. The vertical stabilizer instantly separates and is hurled over 200 feet away. The tail section containing the rear flight recorder and emergency locator transmitter embeds itself in the wall of Building A almost simultaneously. The right wing scrapes the roof of nearby Building B, causing it to detach from the fuselage. Pieces of this wing are found scattered near Buildings A and B. The fuselage continues moving forward, and the right engine impacts a solid water tank on the roof of Building A. The engine mount fails, and the engine lodges itself beneath the tank. Most of the right side of the aircraft is now gone. What remains continues moving forward. The left main landing gear and left wing impact the main wall of Building C, causing it to detach from the fuselage. The left engine detaches from the casing due to this impact and is thrown forward near the ground floor of Building D because the plane was full of fuel. The impact causes an almost instantaneous explosion, reducing a perfectly functional aircraft to mere fragments in 2.5 seconds. So, this is the sequence of the accident. But the big question is what actually happened during the takeoff phase that caused the plane crash. The first step in any accident investigation is to locate the 2 black boxes. The Boeing 787 carries 2 enhanced airborne flight recorders. One mounted in the front and the second mounted in the tail. Although both were recovered within days of the accident, the tail unit, which absorbed all the force of the impact with Building A, was destroyed due to extensive thermal damage and the data was unrecoverable. The front recorder survived. To extract data from the damaged front recorder, A and B needed an identical working chassis to place a memory module before reading it. This is called a gold chassis. However, A and B didn't have a gold chassis, nor the cables to do the job, so they had to import it from the NTSB in the United States. Now I want you to think about that for a second. India operates dozens of 787s. Air India alone has over 30 in its fleet. Yet, the country's Aviation Accident Investigation Bureau doesn't have the capability to download data from a flight recorder of one of the most common aircraft types in the world. Interpret that however you want, okay? So, now it's time for the simulation. I've already mentioned that we found something that doesn't match what the preliminary report says, but for you to believe the data, I need to gain your trust that the simulation is actually correct. And the best way to do that is to show you how we simulated the flight path. I had a lot of fun doing this, so, like it or not, I'm going to show you how I did it. We've already modeled the entire airport, runway, and aircraft in 3D. Now we need to know what the real flight path is. To recreate the flight path, we need to know how the real AI-171 flew that day. And for that, we'll use this CCTV footage as our reference. The problem is that it's very shaky, so to make it usable we first need to stabilize it. I did this using Photoshop frame by frame, which gives me the actual position of the plane in each frame. But to now be able to combine the 3D plane with this image, I need to see through a virtual camera that matches this camera. And then I need to know three things. Where was this CCTV camera positioned in the real world? What type of camera was it so I can find the sensor size and at what focal length the camera was filming? To find out where the camera was positioned in the real world, I used this watchtower, these road markings, and this gate and cross-referenced the references with Google Maps. If you look closely at the footage, you can see a security camera mounted on a pole at a height of about 15 feet. Our camera is probably mounted on a nearby pole at a similar height. So, I used a tool called FPY to triangulate the exact location of the camera right here. Second, I need to know what kind of camera it is so I can find the sensor size. Again, from this footage we know we're working with a PTZ camera. And after searching YouTube for a long time, I finally found this footage from the Elite Aviation channel showing a close-up of the camera used at Ahmedabad. Searching further on Google, I discovered that the cameras used at Ahmedabad are made by a company called Infinova and the sensor size they use is approximately half an inch. The third unknown is the focal length. And getting that was the tedious part. Since it's a zoom camera, it could be anything. So it was a manual process of locking the camera in place and playing with the focal length of the virtual camera until a 3D environment matched the source footage. And once the camera was locked, I matched the 3D plane in each frame with the position of the real A171 in the footage, and that gave me the recreated flight path. To validate the flight path, I used the second image, the RAT photograph from the provisional report. From this camera position, again, there's a good match with the ground plane, the background terminals, and this tower. And if I navigate, you can see that the 3D aircraft matches almost exactly the aircraft in the image. Now we have everything we need to know about how this aircraft flew that day. The simulation runs at 30 frames per second, so each frame is 1 second. We'll start with the takeoff run.
Air 171, winds 246, runway 23, cleared for takeoff. Cleared for takeoff, runway 23, Air 171.
The takeoff run begins at 13 hours 37 minutes and 37 seconds. First Officer Kander advances the power levers and both engines smoothly accelerate to takeoff power. The flaps are set to 5, the standard setting for a Dreamliner takeoff. This is confirmed by the wreckage as well. From the simulation flight path, we can calculate the ground speed and altitude of the aircraft at any given frame. And given that the wind that day was 240 to 5 knots, we can also calculate the indicated airspeed at each frame. I exported all of this to an Excel spreadsheet and used it in the simulation. We'll start by reviewing the chronology as per the official report, and then I'll introduce my findings and raise some questions. So, the aircraft begins its takeoff run at 13 hours 37 minutes and 37 seconds and continues gaining speed for the next 56 seconds until frame 539, at which point it reaches V1 speed of 153 knots. V1 is the speed at which the aircraft now has to take off, as there is not enough runway remaining to safely stop. 2 seconds later, frame 599 is VR, and the nose wheel begins to lift. The preliminary report states that the speed at this moment is 155 knots. Our simulation is 154 knots. So far, the data agrees. It takes another 4 seconds until frame 668 for the main landing gear to lift off the runway. The weight on the wheel sensor now transitions the aircraft from ground mode to air mode. The aircraft then continues climbing normally for the next 3 seconds, and then at 13 to 382 the aircraft reaches its maximum speed of 180 knots. Immediately after that, the fuel cutoff switches for engine 1 and engine 2 move to the cutoff position. 5 seconds after that point, at 13 hours 38 minutes and 47 seconds, the engine start turbine begins to produce hydraulic power. Somewhere between these 2 points, one pilot asks the other, "Why did you shut it off?" And the other pilot says he didn't. 5 seconds later, at 13 hours 38 minutes and 52 seconds, the left engine switch returns to the run position, and another 4 seconds later, the right engine switch returns to the run position as well. And then the Mayday call was given at 13 hours 39 minutes and 5 seconds. So that's what the preliminary report says happened. I want to draw your attention to this frame here, 758, specifically to these three events. The report says the plane reaches a maximum speed of 180 knots and immediately afterward both engine switches are shut off. But intuitively you would expect the speed to stop increasing once the engines are shut off? Not before, right? This plane is accelerating at takeoff power. Takeoff power is the maximum power the engine can produce. In this configuration, I find it strange that the report states that maximum speed was reached before the engine shut down. And this was the whole reason I wanted to simulate the accident in the first place. And the simulation seems to confirm my suspicions. According to this simulation, as the plane rolls down the runway, the sim speed matches what the provisional report says up to frame 758 at 180 knots. But after that, instead of slowing down, the plane Dame actually continues accelerating for the next 5 seconds up to frame 900, to a speed of 196 knots. The moment of takeoff causes the aircraft to gain altitude up to about frame 100, to a height of 230 feet. Inside a jet engine, once the fuel is cut off, the power will collapse almost instantly. Any high-pressure gases remaining in the engine will be expelled. So this cannot be any residual power pushing the aircraft forward. I thought a lot about this, but I couldn't find an explanation for why the aircraft would continue to increase in speed for 5 seconds after the engines shut down. And the preliminary report states that maximum speed was reached before the engines shut down. So, I'm putting this out there for the experts watching. What could create this 5-second increase in IAS after the cutoff? If you work with jet engines, performance, or flight testing, I would really like to hear from you. And now this brings us to the fuel cutoff switches themselves. What exactly happened here? To understand this better, we need to address 4 different theories. First, the switch was intentionally moved to the cutoff position by someone in the cockpit. Second, the key was accidentally moved by someone in the cockpit. Third, a software feature caused both keys to trigger and move to the cutoff position automatically without pilot input. And fourth, the keys never moved to the cutoff position and some other system on the plane caused the engines to fail. Let's start with theory 4 and work backward. This theory states that the keys never actually moved to the cutoff position and that the engines simply failed for some other reason. To explain why this doesn't hold up, let's use a simple analogy. Your cars also have black boxes. Imagine your car is running. If you turn the ignition key to turn it off, the black box registers 2 things. Ignition off, true. Engine off, true. But if your car runs out of fuel and the engine dies on its own, only one thing is registered, engine off. True, there is no input for ignition because you never touched the key. The same logic applies to the Boeing 787. The flight's black box shows an input for the fuel cutoff keys being moved to cutoff. And here's the important part. If you look at the wiring diagram, there's only one data line labeled RDC, which goes directly from the physical switch to the flight recorder. Its sole job is to record the actual physical position of the switch. The way it does this is that every second the flight computer will check what the switch's status is and record it. That 1 second is called the sampling frequency. So, if the recorder shows true cutoff, that means the switch itself was physically in the cutoff position. There's no software trick or false signal. This is a direct mechanical reading, which means we can rule out theory 4. The switches really did move to cutoff. Now let's look at theory 3, that a software feature in the aircraft caused both switches to trigger cutoff on their own, without any pilot input. This specifically refers to TCMA, the Power Control Malfunction Accommodation. This is a software feature in the aircraft that will automatically reduce power to an engine or even cut it off completely if it believes the engine power is exceeding safe limits. This has happened before with the Aloni's 787, but that was during the landing phase and the plane landed safely. The question to answer is, could the TCMA have triggered the engine shutdown on Air India 171? Here's the wiring diagram for those cutoff switches again. Besides the data connection, the only other circuit for the two switches is a relay with only true and false status. There is no wiring for the switches that would be able to trigger it to automatically move it to the cutoff position based on a software trigger. The other thing about the TCMA is that the TCMA does not work through the cockpit fuel switches in any way. Instead, it physically closes a high-pressure shut-off valve deep inside the engine, cutting off the fuel supply directly. Once this valve closes, it cannot be reversed by the pilots and requires maintenance action to reset the system. This is exactly what happened with that ANA 787. The pilots were unable to restart the engines and the plane had to be towed to the gate. But in the case of Air Incheon 171, we know that the engines successfully restarted later in the flight based on the events here. If the TCMA were the root cause, the engines could not have restarted. So this is not a TCMA failure, and so we can rule out Theory 3 as well. And that leads us to Theory 2, accidental activation. The switches have 3 levels of protection to prevent accidental activation. First, the switch has a spring and so it needs to be pinched and lifted against the spring pressure to move it. Second, there are raised guards near the switches to prevent the hand from accidentally touching them. And third, there are mechanical stops near the base that also prevent accidental activation. Now, somehow, even if an accidental movement occurred, I would expect one switch to have moved accidentally. I have difficulty seeing how both switches activated accidentally with a 1-second interval. So, I'm going to put Theory 2 as improbable. This leads us to Theory 1. The most prevalent claim in the media against this theory is that it's impossible for these keys to be moved manually within a second of each other. I'm not sure where this theory originated, because instead, here's a video of Farid Namebrando that definitely shows it's possible to do exactly that. This is the only theory I have no arguments against. Let's also briefly discuss why the landing gear wasn't retracted, which seemed to be a major point of contention in the media. For the landing gear to be retracted, the monitoring pilot needs to verify a positive rate of climb. This means the monitoring pilot observed that the aircraft is gaining altitude without problem. Only after the positive rate of climb is ensured is the gear up call given and the gear is then retracted. Now, if the first engine started to decelerate on frame 758 and the aircraft at this point is only 55 feet from the ground, this simply isn't enough time to verify that a positive rate of climb has been achieved. So, a gear call would never have been given. And then the gear remained extended for the rest of the flight. Okay, I'm recording this much later and this might sound like a slowpoke, but initially I didn't want to include it, but I'm going to include it anyway. I want to talk about the 2 black boxes and the emergency locator transmitter. Now, the ELT is a device that sends a radio signal when there's an accident and is used by rescue teams to pinpoint where the accident happened. So, look back at something like J-Man Wings 9525 or MH370. In those cases, they tried to pinpoint where the accident happened based on that signal, but in the case of Air India 171, the emergency locator transmitter simply didn't work. The preliminary report only has one line that says the ELT never activated. If the ELT didn't work, there are 2 reasons why it might not have worked. One is that the pilots never armed the ELT. There's a switch on the overhead panel above the first officer where the ELT can be in a reset position, an armed position, or the on position. If the ELT is put in the reset position, the ELT won't work, but it's quite unlikely they would have left it in reset. The most plausible explanation is that, given the ELT is mounted right next to the rear black box, the ELT suffered very similar damage to that suffered by the rear black box. What bothers me here is that the black box and the LT are designed for a specific purpose. They are designed to survive a crash. This impact was a low-speed, low-altitude crash. And yet the black box and the LT, whose sole job is to survive a crash, did not survive. And I really want to know in the final report why this happened. This simulation is an honest attempt to try to piece together what may have happened on that fateful day, given the limitations of the footage and preliminary report available to us. This was a learning exercise for me and something I wanted to share with the community.
Some cookies.
So, like, what do you think, huh? Well, what I get out of this is he's blaming it on the pilots. And I don't believe that they did it. Have a look at it. Pass it along, and thanks for listening.